Imagine the perfect vacation. You are standing on the balcony of the 15th deck of a modern cruise megaliner. Below you are gleaming pools, ice rinks, 1,000-seat theaters, and entire shopping streets. This floating resort towers 60 meters above the water, dwarfing any ship of the past with its sheer size. It seems humanity has finally conquered the ocean, turning it into an obedient backdrop for its leisure. But this illusion instantly shatters when the color of the sky turns to lead and the barometer begins to plummet. The ocean has not changed since the days of the first seafarers. It remains the same, ruthless, unpredictable, and destructive force, capable of generating waves the size of multi-story buildings. And it is precisely in these moments, when the entertainment ends and the fight for survival begins, that the fundamental, terrifying difference between how ships used to be built and how they are built now is revealed. Today, we will not just tell another story about a storm. We will look under the plating, study the blueprints, and break down the naked engineering truth. We will compare the true kings of the ocean, classic transatlantic liners, with modern floating hotels. Why did old ships, despite their smaller sizes, slice through the most terrifying North Atlantic storms like scalpels, while modern giants are forced to flee from the slightest bad weather? This is a story about hydrodynamics, metacentric height, commercial compromises, and what happens when the architecture of comfort collides with the pure fury of nature. To understand the scale of the problem, we must return to an era when a ship was created not as a hotel, but as a vehicle whose sole purpose was to transport passengers safely and quickly from point A to point B, across one of the most dangerous regions on the planet, the North Atlantic. Look at the blueprints of the SS United States, the triumph of American shipbuilding. Its design is a masterpiece of paranoid safety and military expediency. The hull of this vessel is radically different from anything you see in cruise ports today. This is a true ocean liner. Its main weapon against the elements was its length-to-beam ratio and a deep draft, which was 9.5 meters. With its relatively low superstructure profile, these 9.5 meters underwater acted as a perfect counterweight monolith, keeping the center of gravity as low as possible. Liners of the past had narrow, razor-sharp bows designed to cut through waves, not roll over them. A vivid example of this design's endurance was witnessed by the world in January 1968. Then, the SS United States encountered a brutal winter storm and subsequently found itself in a real ice trap. The ship was covered with a thick layer of ice and grew immensely heavy, but thanks to the unique lines of its hull and the colossal power of its engines, the liner was able to break the icy grip and confidently continue its course without critical damage. Engineers of that time faced colossal challenges: how to maintain the strength of a steel hull without making the ship so heavy that it lost stability. The answer was found in the use of materials. On the SS United States, a revolutionary solution was applied. A massive, heavy steel hull was combined with superstructures made of aluminum alloys. This allowed for a drastic lowering of the center of gravity. Think of a roly-poly toy. It is impossible to tip over because all its weight is concentrated at the very bottom. Classic liners were built on the same principle. Their heaviest elements, giant steam turbines, boilers, fuel, and fresh water reserves, were located deep below the waterline. When such a ship encountered a fierce storm and was tilted by wind or wave, the laws of physics instantly pulled it back to a vertical position. The metacentric height, the distance between the center of gravity and the metacenter, was calculated so that the ship would return to an even keel quickly and rigidly. It wasn't very comfortable for the passengers. The rolling was snappy and sharp, but it guaranteed that the ship would not capsize. Theory is one thing, but how did these ships behave in actual combat with the elements? April 1966 gives us an exhaustive answer. The Italian transatlantic liner Michelangelo, a masterpiece of design and engineering, the last of the great express liners, was heading to New York. The weather in the Atlantic was terrible, but for a ship of this class, it was considered normal working conditions. Suddenly, amid the usual storm waves, a wall of water rose before the bow of the Michelangelo. It was a rogue wave, an anomalous ocean phenomenon over 20 meters high. The impact was apocalyptic. Thousands of tons of water crashed onto the forward part of the ship. The waves smashed through the aluminum superstructure, crumpled thick steel hull plates, blew out armored glass portholes, and flooded the forward cabins. The devastation looked catastrophic. It seemed the ship was doomed. But what actually happened? The Michelangelo shuddered, shed thousands of tons of water, and kept going. The deep-seated steel hull did not even come close to the critical point of structural failure. Watertight bulkheads contained the flooding. The specific shape of the bow, though mangled by the impact, did its job. It sliced through the mass of water, preventing the wave from completely crushing the ship beneath it. The structural rigidity, laid down at the design stage, saved thousands of lives. It was a victory for steel, welded and riveted in anticipation of the worst-case scenario. They built ships that could survive taking a direct hook from the ocean itself. Now let's fast forward to our century. The demand for sea travel has changed. The modern passenger doesn't want to cross the ocean quickly. They want to spend time comfortably on board. This led to a complete revolution in naval architecture. A modern cruise ship is not an ocean liner, it is a cruise ship, and the difference between them is fundamental. Instead of a sharp, deep V-shaped hull, modern giants have a wide, almost flat bottom. Their draft is relatively shallow, about 8 to 9 meters, allowing them to enter shallow tourist ports in the Caribbean. But on this flat bottom, engineers erect literal skyscrapers, 15 to 20 decks high. The massive surface area of a modern liner superstructure acts as a gigantic sail. When a storm wind of 100 kilometers per hour picks up in the ocean, it presses against this colossal wall of metal, glass, and plastic with thousands of tons of force. So what keeps this skyscraper from toppling over? First, the immense width of the hull. Modern cruise ships are built incredibly wide. Second, active fin stabilizers, extendable underwater wings that work like airplane ailerons, automatically changing their angle of attack to compensate for the ship's roll. But here lies the ultimate engineering trap. These systems are designed for passenger comfort, to keep the martinis from spilling during a gentle swell. They are ingenious, but they do not make the ship invincible. Moreover, a high center of gravity means a modern liner has a much lower margin of stability in extreme conditions compared to old ocean liners. If the computerized stabilization system fails in a severe storm, or if a wave strikes the broadside at a bad angle, the massive windage area begins to work against the ship. What happens when modern comfort architecture collides with the true wrath of the ocean is perfectly demonstrated by the incident with the liner Viking Sky in March 2019 off the coast of Norway. This is a classic modern cruise ship that was caught in a severe storm. Due to extreme pitching and rolling, sensors detected a drop in oil pressure, safety automatics triggered, and the engines suddenly shut down. The massive vessel, with its colossal windage area, completely lost propulsion and became a plaything for the waves. It began drifting straight toward the rocky shore. Imagine the terror. Luxury furniture flying across the lounges, glass panels cracking, passengers being thrown from side to side, and the crew powerless because a ship without power cannot fight the wind. Only a miracle and the desperate dropping of anchors saved the multi-thousand passenger liner from a massive catastrophe. Physics forgives no compromises. The vulnerability of the high superstructures of modern designs is clearly manifested not only during a loss of power, but also from a direct hit by the elements. Let's recall another telling incident involving the modern cruise ship Grandeur of the Seas. This happened in 2005 during the infamous Hurricane Wilma. Grandeur of the Seas, a magnificent modern vessel with a displacement of over 70,000 tons, encountered the outer bands of this powerful hurricane. What happened? Wind and waves slammed into its towering superstructures. Unlike the Michelangelo, which sliced the wave with its bow, Grandeur of the Seas felt the full force of a broadside impact against its massive windage area. The impact was so severe that the ship sustained significant damage. A wave blew out windows and breached the plating on the lower decks, flooding cabins. Even the thick steel hull plating in the bow section was damaged. Passengers endured hours of absolute terror. Why did a modern ship suffer such damage in a situation that an old transatlantic liner could have passed through with far fewer problems? The answer lies in the materials and weight distribution. Modern ships use thinner sheets of high tensile steel for superstructures to minimize top weight as much as possible. Furthermore, the presence of massive panoramic windows, balconies, and atriums compromises structural integrity. It is like comparing the strength of a solid brick wall to the glass facade of a shopping mall. Both stand firm under normal conditions, but when a hurricane hits, the difference becomes obvious. Cruise lines know about this vulnerability. That is exactly why modern captains have strict orders. Avoid storms at all costs. Their bridges are equipped with state-of-the-art meteorological radars, and at the slightest threat, the ship alters its course, even if it means skipping a scheduled port. Their safety is based not on the ability to withstand the ocean's punch, but on the ability to outrun it. So we have come to the main question. Are modern cruise ships safe? Yes, they are incredibly safe, but only as long as their weather forecasting systems work, as long as their engines function to let them outrun bad weather, and as long as their active stabilizers have electrical power. They are the children of an era of technological optimism. Engineers bet that we could outsmart nature using radars and satellites, but the ocean is an element that does not tolerate hubris. Any mechanism can fail. Radars can be wrong. Rogue waves, as we know from the history of the Michelangelo or modern cruise ships in northern waters, appear suddenly, out of nowhere, even in relatively calm seas. The classic ocean liners of the past, with their heavy steel hulls, deep draft, and low center of gravity, were created under a different philosophy. The ocean cannot be outsmarted. Its blow must be taken and survived. Their architecture was the architecture of survival. Modern cruise ships are masterpieces of entertainment architecture. We are witnessing a paradoxical situation in shipbuilding. Ships are getting bigger, taller, and accommodating thousands more passengers, but their physical ability to withstand extreme marine elements is proportionally decreasing. Engineers balance on the thin line between profitability, maximum number of cabins with balconies, and the laws of hydrodynamics. The next time you look at photos of a modern cruise giant in port, pay attention to its proportions. Look at this enormous wall towering over the water. And then remember the sleek, aggressive lines of the old liners. It's not just a difference in design, it is a difference in respect for the power of the ocean. Steel versus plastic. Functionality versus luxury. The ability to survive versus the ability to entertain. The evolution of shipbuilding took the path of comfort, leaving the era of unyielding steel titans in the history books. But the ocean's laws of physics remain unchanged, and the only question is when nature will once again decide to test the durability of our modern floating city.